Okay, this is section 3.2, exponential and logistic modeling. And so we remember that our exponential function takes this form. Y equals AB to the x. So we're going to change that just slightly into a function form. So A was the y-intercept. We're now going to call that P0 for P stands for population, or you can use this for anything. You can use this for money. P is principal. But P0 really means initial amount. So this is whatever I start with. The 0 is about the time of 0. Lowercase t is a time. See if I can write amount legibly. Initial amount. Hopefully I'm spelling amount correctly. Then we do 1 plus r. R does have to be as a decimal. This whole thing here is called the growth factor. If it's a decay factor, it would be 1 minus r. So I could put it as plus or minus. So growth would be plus, decay would be minus. If it's 1.2, the growth rate, if the growth factor then is 1.2. And actually, let's do some of these. So example 1 has me doing a couple of these. So the population for San Jose is given by this. And this is a population that we had from section 3.1. So my initial amount here is, initial amount I'm going to underline in blue, that's 782,248. My growth factor, I'll underline in purple, is 1.136, meaning my growth rate, R, so here I could say 1 plus R is 1.0136, and I just subtract 1 from both sides, and I get R equals 0.0136. When I convert to a percent, I move the decimal to the right 2 places. So I could say that is 1.36% each year. That's how much the population grows each year, which is quite a bit for a population. So Detroit, on the other hand, the population is modeled by this exponential function. This, the b here is less than 1, so this is decay. So my initial amount is 1,203,368. And my decay factor is 0.958. So if I want my decay rate, it's 1 minus r equals 0.9858. I'll subtract 1. R equals 0.0142. Or actually, negative r equals negative 0.0142. So my decay rate is 0.0142, or 1.42%, is how much quickly Detroit is losing its population every year. Okay. Example 2 has us do about the same thing, but we're taking initial value 12, increasing at a rate of 8. So writing the function, P of t, initial value is 12, that goes here. Increasing at a rate of 8% is 1 plus 0.08 to the t. I should simplify this to 12 times 1.08 to the power of t. Okay. Using this to model a function, this was ex2. Example 3. Suppose a culture That looks bad. Suppose a culture of 100 bacteria is put into a petri dish that doubles every hour. Predict when the bacteria will reach 350,000. First thing is going to be to write the formula. Start with 100, that's my initial amount. Doubles would really mean 2 to the power of t, or 2 to the t. So yes, I could kind of use this form 1 plus 1. Doubles means multiplying by 2 every time. Halving would make this decay factor a half. So now if I want to find when it equals 350,000, because you don't know how to use a logarithm yet, you're going to have to do this with a calculator or with a graphing calculator. So we can solve by graphing, but I want to make my life a little easier, so I'm going to divide by 100 first. Make the numbers I have to add a little smaller. 3,500 equals 100. Nope, not 100. That goes away. 2 to the t. So I'm going to go over the graphing calculator. I'm going to graph both of these. Actually, there's kind of the easiest way to often solve by graphing. Yes, option 1 is to do y1 equals 3,500 and y2 equals 2 to the x. Does have to be to the x. Option 2 is to solve this and make it equal to 0. I like this option because it doesn't involve as much rezooming. Although I might do both. So if I'm really looking just to solve it, I'm going to do that. I think I want you guys to see the graph, so I'm going to enter the first one. Now I know I'm going to have to adjust my window. Doesn't need to be that much, probably 20. I need to be more than 3,500, so I'm going to go 4,000. And I can see my intersection. I go to second calc, or second trace gives me the calc, and I want intersect. 11.77. So the 12th hour, it will get over 350,000. So my solution is t equals 12. Another type of modeling that we do a lot, and it's pretty common in pre-calc, we like to do it, is the half-life problem. So half-life, your decay factor is going to be half. So suppose the half-life of a certain radioactive substance is 20 days, and there were 5 grams initially present. Find the time when there will be 1 gram of the substance remaining. So, half-life equation. We'll just call it S of t, substance, the amount. Initial amount was 5, 1/2. Because the half-life is 20 days, I'm going to take my time. Instead of making it half-lives, I want it to be days. So I'll do t divided by 20. I know that it's going to initially be this. So I'm trying to figure out my function is right here. It asks me when will there be 1 gram left? again, to solve, I'm going to go with the graphing calculator. I think this will be in the no, be in the 50s, probably. Less than 3 half-lives, but I'm going to use 0.5 because it's calculator. Window, I think I need to go to 50. This doesn't need to be greater than 10 because I started at 5. Oops, I forgot something. It's 0.5 x, and that exponent, I need to divide it by 20. And it looks like it's just past 50, or just before 50. $46.43. That is the number of days. So that's when it will cross and be below 1 gram after that. So during the 46th day or before the 47th day, they converted it to hours in the book, 46 days, 11 hours. We can do another example. And we're going to talk about atmosphere. That was example 4. Atmospheric pressure, also an exponential function. Find the altitude above sea level when the atmospheric pressure is 4 pounds per square inch. We know, there's a couple of things we know, and we're given this before the example. 14.7 pounds per square inch is the atmospheric pressure at sea level. We know it is half of that at 3.6 miles. So quite a bit higher than Denver. 3.6 miles, that's something like 20,000 feet. So at the top of Denali, that's the tallest mountain in the lower 48 states. It's in Alaska. It's about 20,000-ish feet. Somewhere around there, it's going to be half of 14.7, which is 7.35. So I know it halves every 3.6 miles. It asks, when will it be 4 pounds? So my P of T I'm going to use for pressure this time is 14.7. I know it's halving. H, or not P of T, I should do P of H. Go. And because H is halving every 3.6 miles, I'm going to put 3.6 up here. So I want to know when it's 4. Again, I'll use my graphing calculator. This can be solved with a logarithm, which we'll learn more about in a couple days. But we can solve it by graphing calculator for now. So I'll enter my 2 functions. Need 4. Take my window. Probably isn't that high. But we're gonna go 20 here because it starts at 14.7. Doesn't matter that much where the intersection is, as long as I can see it. Guess doesn't matter if there's only one intersection. So 6.759, 6.76 miles high is when the atmosphere falls below 4 pounds per square inch. That's pretty darn high. That's taller than Mount Everest. Yeah, that's taller than Mount Everest. Had to think about that for a second. But that's really low oxygen levels. Okay, we are going to talk a little bit about modeling some data. We're moving to example 6. I'm going to clear these out for now. And we're going to model data with a table. The example 6, the data is on page 293, and I already entered it into my calculator. So here I've got the data from 293 and L1 and L2. It says use the 1900 to 2000 data in table 3.7 and an exponential regression to predict the US population for 2003. Compare the results to the listed for 2003. Now I set 1900 to be 0. It was a nice easy round number. I don't really like my y-intercept at year 0. It doesn't tell me much because these trends have not continued for 2000 years. The trend goes from about 1900 to 2000 because there was no US in 00. So we're going to do an exponential regression to get an exponential model. But first I want to look at my model. So I'm going to go stat plot. I'm going to turn it on. I want L1, L2. And type is set to scatter, so that's good. I will go zoom. Stat is 9, so I'm just going to hit the 9 button. And it finds it. That's great. Now let's find my model. Exponential regression. I'm going to go stat. Scroll over to calc. I'm going to scroll down until I see EXPREG. Stands for exponential regression. X list is L1, Y list is L2. Store regression equation. I'm going to make this Y1. Y vars function Y1. Go down and calculate. So my function here is Y equals 80.87 times 1.0128. I'm keeping 4 decimal places to the X. Got to keep a lot of decimal places. Little bits with exponentials get off quickly. So it wants to know what 103 would be. So I'm just going to enter that. $80.87 times 1.0128. I didn't mean to start over. To the power of, it asked me to predict 2003, which is 103, 299.72, which is a little higher than 290.8. I can look at the graph again because now it should have the line on it. We can see I'm just a little over my dot. So that looks like my prediction was correct. Oh, they did in the book, they kept another decimal place. Wonder if I have a data entry here because I did not get the same number that they did. Let's look at my 92.2, 106, 123.2, 132.2. I don't see my error. Usually if I don't get exactly what the book has, it's my error. I don't see my error. Let's double check that I did everything correctly. Stat, calc. No, that's not what I want. I'm gonna go, I went down to the bottom and back up because I thought it was faster. Yeah, I don't get exactly what they did. Um, but there it is. It's pretty close. So it's a little over either way. Okay. So we talked about logistics and carrying capacity a little bit in the last lesson. And we're going to compare two populations where when I'm talking about logistics, I'm talking about something that's going to have a shape like this on the graph where it has kind of a maximum population somewhere, kind of an upper asymptote. So we're going to talk about the population of Pennsylvania and Florida. Pennsylvania has slowed down how fast it's growing. Florida has increased. You can find that data in example 7. And we're going to make two logistic models. Okay. So again, I've already entered this data. Take some time to enter it in your data. But mine here is in L3, L4, and L5. So I'm going to make two logistic models. Stat, I'm going to go edit. No, I'm going to go over to calc. That wasn't what I wanted. I didn't mean to hit enter again. Logistic. So logistic is logistic regression. I'm going to store this one in Y2 function. I'm going Y2 because I've already used Y1. I do not want L1, L2. I want L3 versus L4. So since I entered the data in L3 and L4, that's what my X list and Y list need to be. Okay. This is important to look at what the model is telling me. My equation, it kind of gives me the C divided by 28.021 over 1 plus 81.90 times 0.04701 to the X. Nope, 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 that's not what it says. It says A and then E to the negative 0.04701 X. This is my logistic model. Okay. If I want to know its maximum, it's 28.021. I can also go back to the calculator. I can see it in Y equals. I'm going to turn off the first one. Go up to my plot. So second Y equals allows me to adjust the stat plots. Instead of L1, I want this to be L3. Instead of L2, I want it to be L4. Now I'm going to do zoom stat again. And it kind of cuts it off. I might have to adjust this. But I'm going to go ahead and compare, put Pennsylvania's on here too. So Pennsylvania, I've entered into L5. I'm going to go over to stat. I'm going to calculate a logistic again. Except instead of L3, L4, L3 is still the X, but L5 here is the Y. I'm going to store my regression equation in Y3. And here's my other equation. Y equals 12.579 over 0.938. No, 1 plus 0.938 e to the negative 0.03431x. There's my second one. Clearly, Florida has a higher carrying capacity. I'm going to come over, I'm going to set up a second stat plot so I can see this. So second y equals, I'm going to plot 2, turn it on, and do L3 versus L5. Do zoom stat again. It's probably going to be in the same spot. Now I'm going to zoom out a little bit so you can see a little bit more of the logistic. I'm going to change my window. X-min. And I'm going to do the one the book used. Scale is, let's do 3. I think they used 1800 in the, yeah, they used 1800 to slide the thing over. So that's why I should use a different window. Negative 110 would show it better. Oh, that would give me the same window they have. And you can see the two logistics. They will meet somewhere in the 1980s. Last thing we're going to do is we're going to talk about modeling a rumor. That was example 7. Modeling a rumor. Again, I pre-entered this function. I'm going to turn everything else off and turn this one on. So this models a rumor. I'm going to go to normal zoom, and that's not even close. And it says Watauga High School, example 8, has 1,200 students. Bob, Carol, Ted, and Alice start a rumor, which spreads logistically so that you have the function y equals, and it's 1,200 over 1 plus 39 e to the negative 0.9x. Models the students who have heard the rumor at the end of t days, where t0 is the beginning of the rumor spread. So if I want to know what it is at 0, I just plug this in. And so I'm going to quit out of this, and I'm just going to plug it into the equation. So 1,200, I'm going to plug in 0. 1 plus 39. E to the any power, e to something times 0 is just 1, because that's e to the power of 0, which is always 1. So 30 people have heard at the end of day 0. The question is, how long does it take 1,000 kids to hear? Well, let's put 1,000 here into Y4. Now I've got to adjust my window. I know my upper limit, it might not be more than 10 days, but let's go to 30. I know my upper limit is probably going to be, needs to be over 1,200. So let's go 1,500, 100 for my window. I can look at it and find the intersect. I don't care that much because there's only one intersection here, 5.85. So within 6 days, 1,000 people will have heard this rumor. Looks like there's only 1,200 kids in the school, so that's probably why that's the max. Okay, that is section 3.2.